Uh,
Okay, Shankar.
yeah, good morning, all. Uh, Thanks for your patience and also joining for the webinar today. Basically, I would like to give a little bit of background before the actual presenter starts the training session. So, as you all of you know, Pi Mathematics is a non-profit organization involved in mathematical related activities, primarily to remove max phobia. As part of that, I'm right, there are multiple channels in which we spread the mathematics. Uh, One is via the structured trainings to group of selected focus students and teachers, and via magazine articles and books. So every year, Pi Mathematics Association conducts a summer students workshop, primarily covering face-to-face discussion. But unfortunately, that external COVID situation, still we don't want to stop those service, and so hence we wanted to do online. So as part of this is the third training. Last 2 weeks we had successfully around approximately 25 students participated in the batch. Right, this is the third training. So now, given that short introduction, I will request Sivaraman, the founder of Pi Mathematics, to introduce the presenter. Sir, over to you.
So I'm pleased to introduce Mr. Kalyankumar. We are Kalyankumar. He has been in our association for the last 5 to 6 years since we know him. He has been a very active member, always helping us in all possible ways. Because whenever we go for any voluntary help, he immediately offers himself to do any help, especially financially. Every year, he is the highest contributor for providing fee to poor students. So he has been very kind to us in doing all possible help. He has also taken some free classes on behalf of Pi Mathematics Association at government school and corporation schools some 2-3 years back. So he has been a very active volunteer. Because he went some 2-3 years to US for his job profile, he could not involve himself during that time. But whenever he is in India, he always volunteer himself to do help. Even last week, he was one of the co-hosts in organizing this webinar. And today we are very happy that he himself is presenting this talk today. He is going to talk in the topic Convergent and Divergent series. When I just asked him, he was little reluctant to accept. முதல்ல கொஞ்சம் யோசிச்சார் வந்து சார் நான் பண்ண முடியுமா அப்படின்னாரு. So I told him that you have good skills. Whatever I observed from him so far is that he had great interest in and passion in learning mathematics. As far as I knew, he have some hundreds of books in his home. Most of them suggested by me, our association. He was very much involved in association activities, and he want himself to project mathematics to next level, which is what the Pi Mathematics Association is also doing. So we are very happy that right person is giving a talk today. He has 13 years of experience in IT industry. Though he is primarily an IT expert, he was volunteering. He knew mathematics to a greater level, and his interest is such that he has finished his post-graduation MSc Mathematics through correspondence course from Annamalai University, which I know because I was helping him quite a bit in doing that. So he is not a man who doesn't have mathematics knowledge. So அதுக்காக தான் இதை பற்றி சொன்னேன். ஏன்னா மேக்ஸ் தெரிஞ்சவர் தான் அவர். And he usually discussed so much of mathematics concept whichever he had doubt with me. What little I know, I used to share with him. So இன்னைக்கு பார்த்தீங்கன்னா particularly 13 June is very special and very happy because he has 13 years of experience. Is giving his first talk on 13. That is the first observation that I can give. And being 13th of June, if you add, see 13th is the 6th prime. So 13-6 is very much connected. 13 is the 6th prime number. 6 is a month today, June. If you add and subtract 6 to 13, you get 7 and 19. And if you take this number 7, 13, 19, they are primes with common difference 6. 7, 13, 19. And moreover, Their product is the famous Ramanujan number 1729. So there is no better occasion than today to present this talk. I pray Ramanujan to have a good life to him and bless him more. So I leave this to Kalyankumar.
Thank you, sir, for introducing me to the audience and also keeping some mathematical facts as always. So I hope I'm audible to everyone. Am I audible? Hello?
Yes, Kalyan, you can go ahead.
Okay. Okay, so I welcome the students and the organizers from PMA to this wonderful webinar session. So the topic of today's webinar session is convergent identities. So as you all know, like in all our mathematics, syllabus, we would have come across series like Fourier series, Maclaurin series, Taylor series. So it's a very fundamental part of mathematics education. So today we will see some examples of series and see what are the types, major classifications of series with some examples. I hope you will learn a lot from this session, and it will be an enjoyable session too. So let's proceed, students. So first we will look at definition of series. Okay. So a series is a sum of the terms of an infinite sequence of numbers. So what we do here is we are, keeping on adding the numbers infinitely. Okay. So for example, you can see the below expression, right? I could hear some noise. Like if every one of you could go on mute, that will be really helpful. If it's not already done. Hello.
Kalyankumar, you have to speak. They can't answer you.
Okay, sir. No problem. So you can look at below example, which is 1 by 2 square plus 1 by square plus 1 plus 1. So means, right? So with this as an example, so we will see some more examples and the major classifications of series. Okay. So now, we go to the classification.
Hello.
So there are many. Yeah, yes, sir. Am I clear, sir? Am I audible? Hello? Hello, PMA team. Am I able to? Am I audible?
Kalyan, a little bit breaking is there in your voice.
Okay. Vijay, is it better now?
Yes, Kalyan, it's better now.
Okay, fine, Vijay. Okay. I switched off the fan. I hope that helps. Okay, students. So so just now we saw the definition. So a series is a sum of the terms of an infinite sequence of numbers, and we saw an example, that is the sum of reciprocals of squares of natural numbers. Okay, and now we are looking at the classification of series. So there are many categories of series. So here we are going to look at the major classification, that is convergent and divergent series. Okay, so when do we say a series is convergent? Okay, a series is convergent if the sequence of its partial sums tends to a limit. That means that the partial sums become closer and closer to a given number when the number of their terms increases. So what do we mean by this, students? Okay, so let's say we have some series like this. So what we try to do here is we take 10 terms, we take 100 terms, we take 1000 terms, and we sum up and find the value. Okay, so this is what is meant by partial sum. So when we are doing this exercise, when we observe that the sum is, tending to a limit, so it is going closer and closer to a particular number, okay, and it is not exceeding that value, okay, so that's when we say that a series is convergent. So the more and more terms you take, okay, the summation value goes closer and closer to that converging value, okay. So that is what is meant by a convergent series. So then what is divergent series? So it is the opposite of that. So here a series is divergent if the sequence of its partial sums does not tend to a finite limit. Okay. So this limit is a term where we would have come across in calculus, right? So here for divergent series, what we do in a similar way, we take 100 terms, 1000 terms, 10,000 terms, we keep on summing up, okay? But if we look at the summation values, they are not, tending to a limit, okay? So as and when we keep on increasing the numbers and taking the summation, okay, it is keeping on going higher than any number, okay? You can exceed, that means you can, the partial sums can exceed any given number, okay? So that means what? So if it is not tending to a finite limit, so the sum tends to infinity, right? So that's what you raise as a question. So does the sum tends to infinity? So obviously, if the limit is not tending to a finite number, so it is going to tend to infinity. So that is what is called a divergent series. Okay, I hope this is very clear to you, students. So we will take some case studies. Okay, we will take some random series and then we will analyze and see in which category they belong to. Okay, whether they are convergent or whether they are divergent. Okay. Okay. So far, is it clear to you, students? So you can broadcast your questions. So you have a broadcast message option if you look at the web page of the webinar. So please feel free to type in your questions, like if you want more clarity or if you have any doubt, I will try my best to answer. Okay. Okay, students. Now we will go to the next slide. Okay. So this is case study 1. Okay. So now we are going to take a very simple infinite series. Okay. That is nothing but sum of reciprocals of natural numbers. So it is like, it goes on like this: 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 plus 1 by 5 plus 1 by 6 plus etc. So what does this series sum up to? So that is what we are going to find out. Okay. So this series is also called harmonic series. Okay, let's see what is the reason behind that. So you can see the picture in my slide. Okay, so these are nothing but the variants of the harmonics of violins. Here you see the waves are 1, 1 by 2, 1 by 3, 1 by 4, so on. Okay, so what does this mean? The harmonic. So we name it as a harmonic.
Kalyan, 1 second.
Yes, yes.
Your voice is very disturbing. It's like breaking.
Okay. I'm not sure like what should be the reason. So let me try to phone connection.
Shall I do one thing? I'll share the file. You use only the voice. It will be better.
Okay, Vijay. Yeah. Okay, that's fine too. Let me stop sharing. Okay.
என்ன ஆச்சுங்க விஜய்?
இல்ல சார் அவரது
சவுண்ட் சரியா வரல.
வாய்ஸ் பிரேக் ஆயிட்டே இருந்தது சார். அதனால ஃபைல் நான் ஷேர் பண்ண அவர் வாய்ஸ் கொஞ்சம் பெட்டரா இருக்கும். ஃபைல் தெரியுதுங்களா சார்?
I'm able to see the PPT, Vijay. So we can go to that case study 1. Yeah, yes. Vijay. Yeah.
Okay, Kalyan.
Yeah, it's better, Vijay. I'm able to see the screen. Thank you. So is my voice better now, Vijay?
Yes, Kalyan, it's better now.
Okay, fine. So, sorry, dear students, I think there was some disturbance in my voice. So Vijay has given a suggestion and hope things will be better from now. Okay. So now let's continue with the harmonic series example. Okay. So now we saw the harmonic series. So that is nothing but the sum of reciprocals of natural numbers. Okay. And we saw that why this harmonic series is named like that. So it is named after the harmonics in music. Okay. So now we are going to see what is going to be the summation value for the entire series. Okay. Vijay, I think I'm still hearing some background noise. I'm not sure from where it is coming.
But now your voice is very clear, Kalyan.
Okay. Okay, if everybody is on mute, that's fine, Vijay. So we will go ahead, okay?
And almost I muted all the participants.
Okay. Okay, Vijay, fine. Okay, students. Oh, so we can go to next slide, Vijay.
Yeah. Okay. You able to see, Kalyan?
Yeah. We can go to next slide.
Yes, I moved.
Okay, yeah. Okay, students. So we now just now we saw the harmonic series, right? So to find the summation value for this series, okay. So what I'm going to do here is I'm going to split the series into groups, okay. So each group will have 2 power n elements, okay, where n is the natural number, okay. So 2 power 1 is 2, 2 square is 4, 2 cube is 8, okay. So we'll have groups with the 2 elements, 4 elements, 8 elements, and so on. So like that, I am splitting the series into different groups, okay. The first term contains 1 element, the second group contains 2 elements, the third group contains 4 elements, and so on, okay. Now, listen carefully, students. So what I am going to do here is, in each group, I am going to look at the last element, okay, and take its denominator and assign it to each of the previous terms in the same group. So let's, for example, Let's look at this third group, okay? 1 by 5 plus 1 by 6 plus 1 by 7 plus 1 by 8, okay? So now the last term is 1 by 8 and 8 is the denominator value, okay? So I'm taking that denominator value and putting it as denominator for all the elements in the same group, okay? Similarly for the second term also. Okay, so now what is going to happen? So if you look at the first series and the second series, so what do you observe, students? Okay, so what are you observing here? So is the first series greater than or equal to the second series? Is it greater than or not? Okay, so if you look at each term, for example, 1 by 3 plus 1 by 4, okay, you look at the corresponding term in the second series, it is 1 by 4 plus 1 by 4, okay. So obviously we know that 1 by 3 is greater than 1 by 4, right? So the sum of 1 by 3 plus 1 by 4 will be obviously greater than 1 by 4 plus 1 by 4, okay. Likewise for each of the terms, okay. The sum of 1 by 5 plus 1 by 6 plus 1 by 7 plus 1 by 8 will obviously be greater than 1 by 8 plus 1 by 8 plus 1 by 8 plus 1 by 8, right? So if you look at this logical explanation, you can observe that the first series summation will obviously be greater than the second series summation, okay? Now we will see what the second series sums up to. So if you look at each of the groups, okay, the sum of the terms is half, okay. 1 by 4 plus 1 by 4 is half, and 1 by 8 plus 1 by 8 plus 1 by 8 plus 1 by 8 is again half, okay. So similarly the series is proceeding. So the second series sum will be 1 plus half plus half plus half plus half and so on. It goes on like that. So this will sum to infinity. So now we want the summation of the first series. The summation of the first series is greater than the sum of the second series. The second series sums to infinity. So obviously we can conclude that the first series sums up to infinity. Okay, so thus we have seen that the harmonic series is divergent. It sums up to infinity. Okay, so this wonderful explanation was given by a French philosopher, Nicole Orisme. So this proof is called Orisme's proof. Okay, so he first showed that the harmonic series is divergent around 1350. So it's many years ago, right? It's close to like 650 years before itself he has proved this. So that's a remarkable thinking at such an ancient time frame, right? Okay. Okay, so we can go to next slide, Vijay. Okay, so now we'll come to the case study 2. So we look at another example now. Okay, so now we look at something called dichotomy paradox. So this dichotomy paradox is one of Zeno's paradox. Okay, you all would have heard of Zeno's paradox. So Zeno is one of the most famous Greek philosophers. So this is one of the famous paradoxes given by him. So let's see what the paradox says. Okay, before an object can travel a given distance d, it must travel a distance d by 2. In order to travel d by 2, it must travel d by 4, and etc. Since this sequence goes on forever, it therefore appears that the distance d cannot be traveled. Okay, so you can just read it in your mind, students, to make an understanding of what is that. So what it says here is, okay, So let's take an object or a person. Okay, so it has, let's say a person has to cover a distance of 1 mile. Okay, to cover a distance of 1 mile, he has to first cover half a mile distance. To cover that half mile distance, he has to first cover 1/4 of a mile. To cover that 1/4 of a mile, he has to cover 1/8 of a mile. So he has to do an infinite number of tasks before he completes this 1 mile distance. So the paradox raises a question whether the person can complete the ride or not, because he has an infinite number of distances to cover. Okay. So that is what is, pictorially represented here. So the person is running towards the flag target, which is 1 mile, and the distance is, divided into half, 1/4, 1/8, and so on. Okay. So obviously, if you think about this, Zeno, the person who gave this paradox, would obviously have known that this might not be possible, because he himself would have covered distances, completed tasks in his lifetime. But then he probably was curious to know, to find an explanation or a mathematical explanation of this paradox and to solve it. Okay, probably that was what his curiosity. So now we'll go to the next slide to see what this paradox actually means. Okay, so now, so to understand this dichotomy paradox, we have to see what the infinite series of 1/2 plus 1/2 square plus 1/2 cube plus 1/2 power 4 and so on sums to. So because these are the distances that the person is going to travel, these are the distances he is going to cover before reaching his target. So let us see what is the sum of these distances. So 1/4 is 1/2 square, 1/8 is 1/2 cube, and so on. Okay. Now, so you would have come across Maclaurin series in your calculus classes. So one famous result is given here. So 1/1 minus x. Okay, using Maclaurin series, we can expand it as 1 plus x square plus x cube plus x power 4 plus so on, where modulus of x is less than 1. Okay, like 1/2, 1/3, and so on. So now we are going to use this to find the summation of our series behind the dichotomy paradox. So in the first series in the slide, right, I'm just going to take half as a common factor outside. So if you look at the terms inside the bracket, it is very much similar to the Maclaurin series expansion, with x being 1/2, which is obviously is less than 1. Okay. So the summation of that terms inside the bracket as per Maclaurin series will be 1/1 minus half, which is 1/2, which is 2. Okay. So what will be the summation now? So it is the half which we have taken outside as a common term into 2. That is nothing but 1. Okay. So now what we are observing is, even though the series, okay, even though the first series in the slide has infinite terms, it sums up to a finite number 1. Okay, so even though the terms are infinite, it sums to a finite number. So that is, it's surprising for us to see that, but that's how mathematics works. So now we got some idea behind this dichotomy paradox, which we discussed in the previous slide. So even though the person is going to do an infinite number of tasks, okay, if you sum up all the infinite tasks, it is just a finite task. Okay, so since the series is finite and converges to 1, we can conclude that the person can definitely travel the distance of 1 mile and he will be able to complete the journey. Okay, so what is curious here is just to see how the paradox was raised, just to understand the curiosity behind the person who raised the paradox and people who gave a solution for this paradox. Okay, so that is worthwhile to note here. Okay, so we can go to next slide, Vijay. Okay, so here, we are going to visually see the same thing. Okay, so whenever we see a theorem or a mathematical fact through a diagram or a pictorial representation, we get more clarity of it. So in a similar way, there are two diagrams here, okay, to explain the same paradox which we just discussed. So you can see on the left hand side, so there are two squares here. So we look at the left hand side square first. So the left hand side square has a side of let's say 1 centimeter. Okay. So now what we are going to do is we are going to continuously split the square into rectangles and squares. Okay. So first split it into two rectangles vertically, each with area half. Okay. Then go to the one half of the rectangle, split it into two squares with area each 1/4. Then go to one of the squares. Again split it vertically into two rectangles. Again go to one of the rectangles, split it horizontally into two squares. Okay. So as we keep on doing this exercise, we can see that the area of these rectangles and squares are getting reduced by half. Okay. So now this is a pictorial way to see that, the right half of the picture, right? So there are, if you look at this square, there are two halves. The left half is one half and the right half is one half. So if you look at the right half, even though we are continuously splitting it infinitely into many rectangles and squares, the total area will be 1/2. So it sums up to half, and thereby the total area of the square is still 1. Okay. So there is a figure, the square to the right side. So that is also another pictorial representation, but it is slightly different in the sense we have nested squares here. So what we do here is we take an outer square of area of side 1 centimeter. We join the midpoints of all the sides of a square and create another square. Then again we join the midpoints of that square and connect them and form another square. And we are repeating this exercise continuously. So we are getting nested squares continuously. Okay. So here also, if you look at all the nested squares and independently take them and sum the areas. Okay. So let's see what will be the area of the inner square. Okay. So outer square is, we know it's 1 centimeter square, the area. If you look at the inner square, right, what will be the area? So it's obviously, it will be half of it, as you can pictorially see. Another way to visualize that is using the Pythagoras theorem. So you can see that the side of the inner square will be 1/√2, and thereby the area will be 1/2 square units, right? That's another way to look at it. So if you take all these nested squares separately and sum up the areas, it will be equal to the area of the outer square, which is 1 centimeter square. Okay. So this is another way to visualize the same concept. So I hope it is clear now, students. So we have gained clarity on the dichotomy paradox. Okay. So far we have seen two case studies. The first one was harmonic series and it was a divergent. It converged to infinity. And the second one, we looked at the series 1/2 plus 1/2 square plus 1/2 cube plus so on. So it was a convergent series. It summed up to 1. Okay. Now we'll go to the next case study. Okay. So here we will see some of the ways of pictorially seeing the summation of the series. So it is visually easy to grasp the concepts. Okay. Now in the case study 3, we are going to look at sum of reciprocals of powers of 4. Okay. So we have the series like this: 1 plus 1/4 plus 1/4 square plus 1/4 cube plus 1/4 power 4 plus so on. What does this series sum up to? That is the question we have. So now we are going to analyze that. So for this, for visually representing that, okay, Okay, let's say a triangle. Let's take a triangle, the shaded, dark shaded triangle of area 1. Okay, 1 square units. Now, let's go to the next slide to see how we can visually see that. Okay. Yeah. So if you look at this, the same diagram, right? So the triangle, the shaded triangle of area 1. So we are, okay, we are creating another nested triangle concept. Okay. So if you look at the largest inverted triangle, right? It has 1/4 of the area of the whole triangle. Okay. So you can see clearly that it is 1/4 of the area of the full triangle. Okay, so that is an inverted triangle shaded in a different color. Okay, now what we are doing is we are continuously creating these inverted triangles, okay, to see what will be the summation of the series. So if you look at the second largest inverted triangle, you can easily see the area is 1/16 of the large triangle. Okay, and so on. So the third largest inverted triangle will be 1/4 cube, 4 cube times the area of the large triangle. Okay. So this is a way to pictorially see what the series is summing up to. Okay. So now, if you look at all these inverted triangles in the center, okay, you can see that there are triangles of equal areas on either side at each level. Okay, so that means if you sum up the areas of all these inverted triangles, it will be 1/3 of the area of the full triangle. Okay, students, we can have a close look at the diagram to visualize that. Okay, so you can see that the largest inverted triangle is 1/4 of the area of the big triangle. Okay. Similarly, the second largest inverted triangle is 1/16 of the area of the big triangle. Okay, so we are repeating this series. So now we have pictorially seen that 1/4 plus 1/4 square plus 1/4 cube and so on is 1/3. So now coming back to our series in question, which is 1 plus 1/4 plus 1/4 square plus so on, the summation value will be 1 plus 1/3, which is nothing but 4/3. Okay. So this series is also a convergent series and its value converges to 4/3. And we have seen it a pictorial way of, understanding this mathematical fact. Okay. Now let's look at another example. Okay, to pictorially see. Okay, so all these the diagrams which I show you, right, in this pictorial representation. So most of them I have taken it from a YouTube channel by name Think Twice. So they have really ingenious ways of representing pictorially the summation of the series. So when you have time, I would definitely recommend you to go through the Think Twice channel in YouTube to see some of these, visually summing up the series. Okay. So coming to our case study 4. So till now we have seen, sum of reciprocals of natural numbers, sum of reciprocals of powers of 2, powers of 4, and so on. So now we are going to look at a different kind of a series. It is alternating series, okay, of powers of 2. In the sense, alternating series, which is given by the summation of the reciprocals of powers of 2. Okay. So the series is like this: 1 minus 1/2 plus 1/2 square minus 1/2 cube plus 1 by 2 power 4 minus and so on. I think I have a plus there. It should be minus after 1 by 2 power 4. Okay. So here we have alternating signs of plus and minus, and we have the reciprocals of powers of 2. Okay. So we have to see what the series is summing up to. Okay. So now let's see. So we have two pictures in this slide. Okay, let's look at the left picture. So what we have there is 3/4 of a square. So we had a square, 1/4 of the square has been cut off and removed already. Okay. Now for the remaining portion, the total area is 1. This total area of 1 is divided into 4 equal parts. Okay, as we have divided the figure. Okay, so there are 4 parts in this 3/4 of a square. Okay, 4 equal parts of this part of this portion. Okay, so now let's go to the series. Okay, what is the second term? The second term is 1 minus 1 by 2. So in this total area of 1, we are going to remove half of its area. Okay, so 2 pink blocks, right? So the 2 blocks are shaded in pink color. So when we are going to shade in pink, that means we are going to remove that area. Okay, we are doing a minus, and the plus terms will remain in green. Okay, so finally we can look at the green areas to see what will be the summation of the series. So we have a total area of 1 of 4 equal parts. Now what we are doing, 2 parts we are removing. So that's what is shaded in pink. Okay, 1 minus 1 by 2. Okay, now we'll go to the third term. So we'll go to the next slide now. So observe carefully, students. So if you observe carefully, you can get the pictorial representation here. So now after we subtracted 1 by 2, the third term is plus 1 by 2 square, which is plus 1 by 4. Okay, so now whatever we removed just now, we are again going to add half of it. So we removed 2 blocks, we are going to add 1 block. So again one pink block became green, right? Okay. Similarly, if you look at the next term, it is minus 1 by 8. So now what we are going to do, again, if you look at the center region, right, the plus 1 by 4 green region, which we just now turned from pink to green, if you look at that region is again divided into 4 equal parts, and of that 4 equal parts we are again removing 2. Okay, so that is what is represented as minus 1 by 8. Okay, so if you observe closely how that, you know, the green areas and the pink areas are changing, you can visually see what the series will sum up to. Okay, in the same pattern we are adding, subtracting. Okay, I hope it's clear to you, students. You can so you can observe the next slide now. It will give you more clarity. So we can go to next slide, Vijay. Okay, thank you. So now what we are doing here is, right, after subtracting 1 by 8, we are again going to add plus 1 by 2 power 4, which is plus 1 by 16. Okay, so again you can see that, you know, of the 4 equal parts we divided, right, we will be adding half of it. Okay, so we are continuing this process infinitely. So you can see that as we are adding more and more terms, okay, so the full area which we started with, right, the full green area, out of that the pink area is removed, right? So the pink area is roughly coming to one third of the total area. So that is what we are visually seeing. as we do this process again and again and again. Okay. So we'll go to the next slide, Vijay. So we will see if we keep on repeating this exercise, what will be the final figure looking like. Okay. So we are adding, subtracting, adding, subtracting. So if you look at all the minus terms, it will represent the pink area in the diagram. Okay. If you see all the plus terms, it represents the green area. So now, after we sum up the series, we will be left with, okay, what is the green area. So the pink area is removed completely. So that pink area is tending to the, is growing more and more towards 1/3 of the total area. So here we have pictorially seen that the series will sum to 2/3 of the area we started with. Okay, we started with the full area as green. So all these pink terms in minus is taking away 1/3 of the area. So we are left with 2/3 of the area. So I hope this example is very clear to you, students. So you can work it out and you can see the YouTube channel which I just mentioned, and you can, you know, learn more about series and also observe more and more examples of these. Okay. So now we'll go to the next example, a little more complicated one. So this is the case study 5. Okay. So I hope all students are able to follow. Please raise any questions if you have, students. Please feel free to, you know, ask your questions. Okay. So let's continue with this. So now we are going to look at another alternating series. Okay. This time we are going to look at powers of 3, reciprocals of powers of 3. So the series will be like this: 1 minus 1/3 plus 1/3 square minus 1/3 cube plus 1/3 power 4 and so on. Okay. So to visually see what this series is summing up to, right? So let's look at the diagrams in the slides. Okay. So we have a square of area 1 as usual. So we are dividing that square into 3 areas, 3 equal areas, each having area 1/3 of the original square. So we are splitting it horizontally. Okay. So now, if you look at the first term in the series, right, it is minus 1/3. So 1 minus 1/3 we can visualize by removing one block out of the 3 blocks. So if you look at the first diagram, 1 minus 1/3 is just the one block removed out of the whole square. Okay. So now whatever the area is removing, it will be in black, and whatever the area remains, it will remain in the dark gray color. Okay, to visually see that one. So now let's look at the third term in the series. It is 1/3 square, which is 1/9. Okay. So now we divided the square into 3 equal blocks. Now let's take each block and again split it into 3 units. So now what will be the area of this, each of these 3 small squares? Okay. So on the first level we had like 3 rectangles, each had 1/3 of the area of the original square. Now we are taking each rectangle, splitting it into 3 squares, right? So now you can easily see that each of these small squares has 1/9 of the area of the big square, right? So each of them has an area of 1/3 square. So when we say we are going to add, that is plus 1/3 square, now what we can do, we have to add one of these small squares, right? So that is what we are going to do now. Okay. So there is in the picture in the second diagram, you can see that there is a region with area marked as 1 by 3 square, right? So we are going to add that square to our summation. Okay, so we'll go to the next slide, Vijay. So now we have added that area to our series. So plus 1 by 3 square is done. Okay, so that one small square is also shaded in green. Now what we are doing is splitting this small square into two triangles and just shifting one triangle to the left to make the shape look symmetrical. Okay, it's the same area, just that we are splitting into two triangles and bringing one triangle to the left side. So now you can see the shape is symmetrical. So now what we have achieved 1 minus 1 by 3 plus 1 by 3 square. Okay, so now we have to repeat this process. So we can go to the next slide, Vijay. So now what we have to do, now fourth term in the series is minus 1 by 3 cube. So again, if you look at the center small square, again we are splitting it into three areas, three rectangles of equal areas. So now what will each of these small rectangles area will be? It will be 1 by 27th of the area of the original square, or 1 by 3 cube of the area of the original square. Okay, so that one we are going to subtract. So subtract in the sense the color will change from green to black, right? So you can see the figure, the diagram to the right hand side. So we have subtracted the 1 by 3 cube. Okay. Okay, I hope it's clear to you, students. If you look closely at the diagram, you can follow the visual fact. So in a similar way, okay, so we are splitting it into equal areas and continuously adding and subtracting. You can see how the figure, the diagram is changing. And one modification is to make the figure as symmetrical. We are splitting the smaller square into two triangles and moving on to the left. Okay, so if you continue the same process infinite number of times, we will get the diagrams in the next two slides. Okay, see here. So now what we have achieved, okay, the similar way you can see here, right? You can look at the center square. In the center square, you can look at the third rectangle from the top. Okay, so what we have done is we have added plus 1 by 3 power 4. So that small square we have added. As before, what we have done, we have split it into two rectangles and taken one rectangle. We have split it into two triangles and taken one triangle to the left to make it symmetrical. So now you can see that whatever the portions we have been removing now, and we are going to continuously remove, that area is resembling a triangle. So if we repeat this process infinitely, the area which is continuously getting removed, okay, will tend to form a triangle whose area is 1/4 of the area of the original square. So what will be left for us will obviously be 3/4 of the area of the square. So we have seen visually that whatever the series we are seeing now, 1 minus 1 by 3 plus 1 by 3 square minus 1 by 3 cube plus 1 by 3 power 4 and so on, it sums up to 3 by 4. Okay, I hope it is clear to you, students. So so it is very easy and for us to understand the concepts when we see visually the concepts, right? Rather than, of course, the same things can be proved using theorems and proofs, but if we see it visually, we will have a different representation, and we can more easily grasp the concept. So that was the motive behind showing you these slides, which we discussed till now. Okay. So far we have seen 5 case studies. So we have seen 5 series. So out of these 5, except the first one, that is the harmonic series, all the other series are convergent series. Okay, they converge to a specific number. Okay, so now, so far we have looked at slides and some small proofs. So now we will do some mathematics. We'll get into some mathematics, but not too complex. I can promise you on that. And we will take another example and we will do some mathematics. Okay, so we can go to the next slide. Okay, now we will look into a different series. Okay, this is what is a series we saw during the definition, if you remember. So now we are going to look at the series of sum of reciprocals of squares of natural numbers. That is 1 plus 1 by 2 square plus 1 by 3 square plus 1 by 4 square plus 1 by 5 square plus 1 by 6 square. Okay, plus so on. So this series, okay, so we have to, our aim is to find the summation of this series. So this series has a special name. It is called the Basel problem. It is a very famous problem in mathematical analysis. So let's look at some historical facts before we go to the solution of this Basel problem. So this problem was first posed by Italian mathematician Pietro Mengoli in 1650. Okay, and the Basel problem was first solved by Leonhard Euler, a Swiss mathematician, in 1734. Okay, so Euler, you students are mathematics students, so definitely you would have come across this great mathematician's name multiple times across different papers. Okay, so Euler, as we all know, is one of the most prolific mathematicians in all of history of mathematics. Okay, and he's from a native of Switzerland. So many of us, Switzerland would be a dream tourist destination, obviously. But it is quite interesting to note that this one of the most prolific mathematicians in all of history, Leonhard Euler, was from Switzerland. It is quite noteworthy to note this point. And also, there are a lot of interesting facts in Euler's life. So I request you students, if you find some time, I request you to read the life history of Euler. And also his extensive works are easily available to the general public. You can search it in even in Google as Euler Archives. His entire volume of published works is available for the general public, and some of his work is also translated in English, and you can see some of his papers in his own handwriting. So when you find time, I request you all to go through the life history of Euler and also the Euler Archives. And another interesting fact to note about Euler is around the middle of his career, he lost sight of one of his eyes. Okay, but he kept on producing mathematical results and became increasingly famous with the mathematical community at that time. And in his later years, he became completely blind. And it is said that even after becoming completely blind, he was extremely productive, and he used to dictate mathematical notes, and his sons and grandsons would take notes of it. That's what I've heard many people say, and I have even read it in some articles. So Euler has he has a very great legacy and definitely he's a great inspiration for all mathematicians to come. So I definitely request you to spend some time on his life history and his work, published work. Okay, now let's go to the next slide. Okay, so to solve this Basel problem, so we are going to take a detour. So we are going to look at some other series expansions. We will look at some other formulae, and then we will come to the solution. Okay, so first thing we are going to look here is the Taylor series expansion of sine function. So you all would have come across this famous result, students, from the Taylor series expansion. Sin x is equal to x minus x cubed by 3 factorial plus x power 5 by 5 factorial minus x power 7 by 7 factorial plus x power 9 by 9 factorial, and so on. So we have alternating signs, and if you look at the powers of x and also the denominators which are in factorials, you can see we have only the odd numbers. Okay, so in typical as an IT student, I would say that this particular series we all have seen a number of times. Write a C program to compute the value of sin x is equal to x minus x cubed by 3 factorial, so on. So we were asked to write computer programs to prove this, to calculate this result. Okay, on a lighter note. Anyway, so in the same series, if instead of x we are taking square root of x, okay, just replacing x with square root of x, we get the second term. Sine of root x is equal to root of x minus root of x whole cube by 3 factorial plus root of x whole power 5 by 5 factorial minus root of x whole power 7 by 7 factorial plus so on. Okay, so now we are dividing the whole expression by root of x. So we will see why we are doing all this. Okay, very shortly we will see that. So if we divide by root of x the whole equation, so we get sine of root x by root x is equal to, the first term becomes 1 obviously because the first term is root of x. The first term becomes 1. So 1 minus root of x whole square by 3 factorial plus root of x whole power 4 by 5 factorial minus root of x power 6 by 7 factorial, and so on. So here you can see that root of x whole square is nothing but x, right? So it is nothing but x power 1 by 2 whole square, which is nothing but x. And similarly, x power 1 by 4 whole power 4, sorry, x power 1 by 2 whole power 4 will be x square, and so on. So now if we go to the next slide, okay, you can see this. Okay, so what we are going to get is, so the same expression, so I am just replacing by root of x whole square as x, and so on. So now we are getting sine of root of x divided by root of x is equal to 1 minus x by 3 factorial plus x square by 5 factorial minus x cube by 7 factorial, and so on. So what we did, so we started with the Taylor series expansion of sin x. We replaced x with root of x, and then we have divided by root of x. So 3 simple steps we have done for now. So now we have to see when this expression becomes 0, right? So we have to find the roots of this equation. So what is the clue we have here, right? So if you look at the middle expression, that is obviously a series. So straight away we are not able to see when the series will become 0. But if you look at the left hand side, there are 2 terms. The numerator is sine of root x, the denominator is root x, right? So obviously x is not going to be 0. We are going to eliminate that condition. So apart from that, we are going to look what are going to be the zeros of this equation. So we have a clue here. So we have the numerator term as sine of root x. Okay. So now we have to just see when the sine function will become 0. So if we find out that, then it will be very easy for us to find the zeros of this equation, right? So, okay. So we will go to the next slide. So let's try to examine when sin x is 0. That is the question before us now. So we have all studied in our geometry classes that sin pi is 0, right? Sin pi is 0. And not only that, integer multiples of pi, if you take all the integer, the natural number multiples of pi and you calculate the sine, it will all be 0. So sin pi is 0, sin 2 pi is 0, sin 3 pi is 0, and so on. So in general, so where n is a natural number, right? So in general, we can summarize that as sine of n pi is 0, right? Sine of positive integer multiples of pi is always 0. So that is the clue, that is a mathematical fact we are going to use here. So now in our equation, we had sine of root x. Okay. So for sine of root x to be 0, what should be the x value? X value should obviously be n pi whole square. So then only x will be n pi. So sine of n pi will be 0, right? So for sine of root x to be 0, x should be n pi whole square, where n is the positive integers or natural numbers 1, 2, 3, 4, 5. Okay. Okay. Now let's look at the next slide. So now whatever we discussed till now, just keep it in mind, students. So we have found out when the sine function is 0 and what should be the value of x. Now we are going to look at another formula known as Vieta's formula, which we are going to use to solve the Bessel problem. Okay, so you would have all read about the theory of equations, right? So let's look at a polynomial equation like this: 1 plus a1x plus a2x square plus a3x cube plus a4x power 4 plus so on plus an x power n is equal to 0. So we have a polynomial equation like this. And note that the coefficient is 1 here. Okay. Now, if this equation has the root, so we know that, if the degree of the equation is n, we can have at most n roots, right? So obviously this equation can have roots x1, x2, x3, and so on up to xn, right? We can have at most n roots. So let's name the roots as x1, x2 up to xn. Okay. So then by the Vieta's formula, we have 1 by x1 plus 1 by x2 plus 1 by x3 and so on up to 1 by xn is equal to minus a1. Okay. So what this means is that if you take any polynomial equation, okay, with the constant as 1 and find its roots, so if we sum up the reciprocal of the roots, it will add up to the negative of the coefficient of x. That's it. Okay. So now we have seen, so this Vieta's formula is named after a French mathematician, Francois Vieta. Okay. So now let's take a simple example and see how this formula works. Okay. Let's go to the next slide. Okay, so based on my personal experience, students, what I feel is right. Whenever I study any theorem, right, if we try to take any sample or any example and try to apply the theorem and see how it works, then it is very easy for us to grasp the theorem. So likewise, when we study it, we just saw a theorem. Now we'll take a small example and let's see how it works. Okay. So let's consider the quadratic equation x square minus 5x plus 6 is equal to 0. Okay. So now to match it with the sample equation, the polynomial equation which we saw just now in the previous slide, we divide the equation by 6 to make the constant as 1. Okay. So in the previous slide, we saw that the constant was 1, right? 1 plus a1x plus so on. So to make it in sync with that, we divide the equation by 6. Now we are getting x square by 6 minus 5 by 6x plus 1 is equal to 0. Now, obviously, so this is a simple quadratic equation. So by looking at the equation itself, we can tell that the roots are 2, 2 and 3, right? So that doesn't change even if you are going to divide by 6. It's still going to remain the same, right? So now we know the roots are 2 by 3, 2 and 3. So now let's try to apply this Vieta's formula. What it says, we have to sum the reciprocals of roots, right? So what is that? 1 by 2 plus 1 by 3. So what is that sum is 5 by 6. So what the theorem said was, the sum of the reciprocals of the roots will be equal to the negative of coefficient of x. So what is the coefficient of x here? 5 by 6, right? Oh, sorry, minus 5 by 6. So what is the negative of that? It is plus 5 by 6. So what is the sum of the reciprocal of roots? Again 5 by 6. So using a simple formula, a simple example, we have verified the Vieta's formula. Okay, we gained an understanding of how it works. Now we have all the concepts ready to go and okay. So now we will go to the next slide. Okay. So now I started. So we did the 3 steps. You remember? We took the Taylor series expansion of sin x. We replaced x with root x, and we divided the equation by root of x. And we stopped there, and then we went to the Vieta's formula. So we take the same equation now again. That is the first equation we have here in this slide. Okay. Now, what we know here is the solution of this equation is given by x is equal to n pi square, right? Because sin of n pi is 0. So, okay. So, what are all the solution? What are all the roots for this equation? So, we can say it as, right, pi square, 2 pi whole square, 3 pi whole square, right? 4 pi whole square, and so on. So, these are all the roots of this equation. So we just substitute the positive integers in place of n. Okay. So now what we have to do as per Vieta's formula, we have to sum up the reciprocals of the roots. So let's do that. So 1 by pi square plus 1 by 2 pi square plus 1 by 3 pi square plus 1 by 4 pi square plus so on. Okay. So that will be equal to the negative of the coefficient of x. So let's look at the equation. Let's look at the equation, the first equation in this slide. So you can easily see that the coefficient of x is minus 1 by 3 factorial, which is nothing but minus 1 by 6, right? So the reciprocals of the sum of reciprocals of the roots will give us negative of coefficient of x, which is nothing but 1 by 6. Okay. Now, if you look at the left hand side, 1 by pi square is common in all the terms. So let's take it outside as a common term. Okay. So then we will have 1 plus 1 by 2 square plus 1 by 3 square plus 1 by 4 square plus so on is equal to 1 by 6. So this 1 by pi square, which we took as a common term, we just take it to the other side. And that's it. We have a solution to the basal problem. So 1 plus 1 square plus 1 by, 1 plus 1 by 2 square plus 1 by 3 square plus 1 by 4 square plus so on converges to pi square by 6. So the sum of the series is approximately equal to 1.644934, so on. So pi square will obviously be 9 point something. So divided by 6, it's roughly 1 by 5 that you can quickly visualize it, right? So the basal problem converges to pi square by 6. So this result was first proved by Euler when he was 28, and then he quickly rose into fame among the mathematical community. Okay. Fine, students. So far we have looked at 6 case studies And out of all that, only the first one, the harmonic series, right, which looked very simple, that is 1 plus 1 by 2 plus 1 by 3 plus 1 by 4, that is the simplest series which we could think of. But only that series was divergent, right? It didn't converge. It is the sum tends to infinity. But all the other series we have seen, even though it looked a little bit complicated than the harmonic series, they all converged to finite numbers. Okay. So now let's look at few exercises for you to try it out, students. I hope you would have learned a lot from this session, and you can try to crack the two exercises on screen. So the first one is sum of reciprocals of factorials. So 1 plus 1 plus 1 by 2 plus 1 by 6 plus 1 by 24 plus 1 by 120 plus so on. Okay. What will be the summation of this series? So you observe in this series there are two ones. So that is because, okay, we have the sum of reciprocals of factorials, and 0 factorial is also 1. So the first term represents that 1 by 0 factorial, which is 1. The second term is 1 divided by 1 factorial, which is again 1. So that is why we have two ones there. I can give you a hint. If you remember the Maclaurin series expansion of e power x, then that should be a cakewalk for you. Okay. And let's look at the second exercise. Alternating series of reciprocals of natural numbers. Okay. So now here also we have the reciprocals of natural numbers, but alternating series. Okay. So 1 minus 1 by 2 plus 1 by 3 minus 1 by 4 plus 1 by 5 minus 1 by 6 and so on. So please try it out to solve it, students. Okay.